All right, last topic, density and temperature. So let's start with density. Density, the equation for density is mass per unit volume. By the way, this is also going to act as a conversion, but we're going to cover that in a bit. So if I have a box, okay, so if I have a box, it has some amount of stuff in it. I'm going to copy this box because we're going to have two of them. Okay, so copy, there we go, paste. All right, so here's my box. And I'm going to put some amount of material inside of them. So this one has three things. This one has one, two, three, four, five. Which one of these is considered more dense? Well, the stuff with more mass, this has five per unit volume. This one has three per unit volume. So three mass per one volume. This has five mass per one volume. Simply said, this one is more dense because it has more stuff inside of it than the other one. So that's more dense. So the more mass is stuffed into the same space, the greater the density. Really important about density. If you need to convert from a mass to a volume or vice versa, you're going to use density for that. Density is your conversion between mass and volume, period. We're going to use it a bunch, but that's what we're going to have it for. So if I see something like this, the density of aluminum is 2.7 grams per milliliter. Again, this is a conversion factor. So 2.70 grams is equal to 1 milliliter. That's what that unit means, grams per milliliter. How many grams are in 63 mils of aluminum? So again, we have a choice. We could use this D equals M over V equation, the one above, but we don't really need to. We can just simply always do these problems as you don't have to rearrange the equation. We're always going to do these as a conversion factor. So write down my original number, 63.0 milliliters times fraction milliliters on the bottom, grams on the top, 2.70 grams per 1 mil. Mils cancel, and 63 times 2.7 gives me 170.1. So we'll talk about two things here. So 170.1 grams is what I got in my calculator. This has 3 sig figs. My answer should have 3 sig figs. So I'm going to underline there. I'm going to round to that. My answer should be 170. We'll put the decimal there because it needs to be there. That's correct. So 170 grams. Great. So again, we're using density as a conversion. Well, how about this next one? What's the density of the metal? Well, in this case, we probably do need to use the equation. D is equal to mass over volume. I have the mass. There's the mass. And there's my volume. I just have to cube it, right? How much volume does 50 grams of water take up? Air, mercury. Well, we have a little table right up here. So let's use this table to determine the different volumes that these things take up, and we'll be surprised by those. All right. Next, let's move on to temperature. So temperature is interesting. We are going to use Kelvin as the K. I don't know why there's an L there. This should be capital K. Temperature in Kelvin. This is the SI-based unit. This is the one that we're going to use. The 3 common temperature scales: Fahrenheit, we use in the US, Celsius and Kelvin. Well, science uses Kelvin. Celsius is used in the EU and pretty much everywhere else. We are never going to use Fahrenheit. So I'm just going to cross that out. We're going to kind of ignore it. You do need to know relative numbers for Fahrenheit. So I know that water boils at 212 for Fahrenheit. I know that the water freezes at 32 Fahrenheit. So we do have to understand those relative numbers, 212, 32, but I don't expect you to know how to do any of these conversions. In fact, I don't expect you to know how to do any of those conversions for Fahrenheit and Celsius, just the Kelvin to Celsius. Well, it turns out Kelvin and Celsius, so 1 degree Celsius equals 1 degree Kelvin. They are the same exact scale. So it's a 1-to-1 ratio. Why is this important? Well, what we see between the two is they're offset by 273.15 or 273. We generally don't always talk about the 0.15. So going from, what we'll notice is if I were to go from the freezing point of the two to the boiling point of the two, there is a difference of freezing point to boiling point. Notice that there's 100-degree difference, 100-degree delta T between those, right? So they're on the same scale. The difference is they're just kind of offset by 273. Why is that? Well, Kelvin, we'll notice, is always positive. We call this an absolute scale. The reason that we need to use Kelvin in science and we need this absolute scale is because negative numbers can cause problems with certain equations. By using a negative number, it can make something go negative, and that's not what we meant to do. So we use Kelvin because it's an absolute scale. It's always a positive value, and that's the reason that Kelvin is used in science. So a couple of things. When I'm converting between degree C and Kelvin, we're simply going to add or subtract, depending on which way we're going, 273. Generally don't need the 0.15, but it's fine to keep it. So 0.15. Okay. Whenever you're converting, just simply remember Kelvin is always greater than Celsius. Okay. So what that means is if you're doing a conversion and you find you did a calculation and you found out that your Celsius number is higher than the Kelvin, you've just added when you're supposed to subtract, or vice versa. So Kelvin number should always be higher than the two. Okay. So convert the following to Kelvin to Celsius, Celsius to Kelvin. So give that a go. Which of the following temperatures is the highest? You'll notice that Fahrenheit is there, but we need to think about that relatively. So I'm going to let you do those two conversions, and we're going to talk about the highest temperature right now. Which one is higher, 200 degrees Fahrenheit or 500 degrees Kelvin? Well, what we want to recognize are a few values. So the boiling point of water is 100 degrees Celsius. If I add that to Kelvin, it is 373 degrees Kelvin, and the boiling point of water is 212 degrees Fahrenheit. The freezing point of water is 0 degrees Celsius, 273, because I'm adding 273 to it, Kelvin, and 32 degrees Fahrenheit. So we're just thinking about relative numbers. So if I'm going to compare Fahrenheit to Kelvin, is this boiling 500 degrees Kelvin? Absolutely, it's boiling. It's well over boiling. So this right now is the higher temperature because 200 Fahrenheit is not even boiling water. So let's compare the next two, 500 degrees Kelvin or the boiling point of water. Well, the boiling point of water is 100 degrees Celsius, so and 373. So this one is absolutely still higher. So we can ignore the boiling point of water because 500 degrees Kelvin is higher. And so now I'm comparing 500 degrees Kelvin versus 150 degrees Celsius. Well, we're going to add 273 to this. So we're going to end up with, 423 Kelvin, I believe. So this one is higher. Sometimes you're going to have to do a conversion, but you can simply look and compare the first to the second, and then the second to the third, and then the third to the fourth. Like, however you do it, just compare them one at a time. Pick a winner, pick a winner, pick a winner kind of thing. All right. So that's it, I believe. Make sure, yeah, that's it. So we're going to take a look at those two conversions. So give those a go, and we'll see if we did it right. But that's it, Kelvin and temperature and density.